All right. So we're we're going to finish up on, in this lecture, we'll finish on our discussion of Galton-Watson processes and move on to another class of branching processes called Yule processes, which actually evolve in continuous time, and we'll show the properties of those processes. So just to remember what we talked about, what we've been talking about are Galton-Watson processes. So a Galton-Watson process is one where we have discrete generations at the discrete time Markov chain, and what happens is so what we have is that we start with one individual alive at time 0 and generation 0, and in the first generation that person or that individual will give birth to some random number of offspring according to some offspring distribution, which is shown here. And that offspring distribution, and then the individuals who are born in the first generation, each one of them, so this individual here and this individual here, they are now independent copies of the original, so they evolve independently of one another, and they give birth at the next generation to a random number of offspring according to the offspring distribution, same offspring distribution here. Okay? And so what this description gives is a self-similarity property, kind of a recursive structure to the process by which at each generation, at each time, the process branches into independent copies of itself. So if we think of this and we look at this tree structure here, we have a genealogical tree of the offspring, random number of offspring of some initial particle or some initial individual, and that gives a genealogical tree of the ancestry or the future generations of that particle. But then if we go one step ahead and we look at the tree underneath the ancestry or the future generations of this individual and of this individual, those are independent of one another, but they are a probabilistic or stochastic copy of the genealogy of the original particle. Okay, and this branching property is one that we can leverage to study properties of the process. And the property that we were most interested in or that we considered so far is the extinction probability. So the extinction probability, which I wrote as zeta, is the probability that the genealogy eventually goes extinct, meaning there's a generation, we reach a generation, some finite generation at which there are no offspring. And since we know that, well, just by the nature of the process, once there's, in order to give birth to any offspring, we need to first have a particle to give birth to them. And so once a generation reaches level 0, it stays 0 forever after, so it will have died out. And so the question of extinction is one of a question of whether or not this random extinction time is finite. And what we showed initially, and we proved last time, is first that the extinction probability satisfies this fixed point relationship with the generating function, and in particular can be described as the smallest root of this fixed point equation. And we further went on to argue that the smallest root of this equation, under certain additional regularity conditions on the offspring distribution, is either, the smallest root is either 1 in the critical or subcritical phase, meaning if the mean number of offspring is less than or equal to 1, then the probability of dying out is 1. So intuitively, why that's the case is, you can imagine, the expected value. So since these are, so you can compute the expected value of the number of individuals alive at generation n. It's a multiplicative process, and we expect that at each generation, the number of individuals alive in the next, or the number of offspring of each of the current individuals alive is mu, and so the expected number of individuals alive at time n is mu to the power n. And so in the case where mu is less than 1, it's intuitive that this should go extinct because our expected number of individuals is decreasing, is decaying to 0. It's actually decaying pretty fast. It's decaying at a geometric rate. So in order for that expectation to be decaying, there must be some probability of dying out. Well, the probability must be 1, because if it wasn't 1, then this shouldn't be decaying. This wouldn't be decaying to 0. It wouldn't be possible. The only really potentially challenging or unintuitive part is the part where we talk about the critical case where mu equals 1. So where mu equals 1, the probability of dying out is also 1. And as we can see in this case, the expected value of the expected size of the generation at time n is actually 1 for all generations n. And so why that should be expected to die out is because we can imagine, well, if that expectation is 1, then we're going to we should be passing or kind of entering into that state infinitely often as the number of generations grows, right? We're just intuitively thinking in terms of kind of law of large numbers. And since this is a multiplicative process, we would have to think about this in terms of, we could think about this maybe in terms of the log of the generation size, which would be mean 0. But what we know from the simple random walk in this case, so for example, I've drawn analogies to the simple random walk, which will cross 0 infinitely often. And in this case, we should expect to be in state 1 or in a state close to 1, so a finite small generation size, a large number of times. But each time we're in, for example, state 1, we have some probability of going extinct in the next generation, just if that one individual doesn't give birth, or if the 2 or 3 or whatever the small number of individuals alive at that time have no offspring. And so if we're in this state infinitely often, we're eventually going to go extinct with probability 1. So that's the intuition there. The final thing that I want to talk about with respect to Galton-Watson processes is the expected time extinction time. And I'm just going to record this. So if we remember, I'm just going to record this here, and the argument that we actually give, the proof that we actually give, relies on techniques that are kind of further along in the course. So I won't actually prove this formally in this lecture. But just to recall some facts, so we have, first of all, we define zeta to be the probability of extinction. So this is the probability that tau is finite, where tau is the first time at which we have 0 offspring. And just recording some of the facts that we've just reviewed, zeta is the smallest root of this equation, where phi of t is the generating function of the number of offspring in the first generation. And what we've shown is that if mu is less than or equal to 1, then zeta equals 1. If mu is greater than 1, then the probability of dying out is strictly less than 1. Now, what we can ask, we can ask what happens, or what is there a difference between the critical and the subcritical case? In the critical case, in both cases, we have probability 1 of dying out, but how long does it take to die out? And so I can record this here, and there's a proof which is in the notes, but I'm going to defer that proof to the notes so that we can move on. The proof is a bit technical in nature. But the first is we're assuming a Galton-Watson process with the usual conditions that we assumed previously, in the subcritical case, mu less than 1, there exists a constant c such that the probability that the extinction time exceeds n is asymptotic to c u to the power n, as n goes to infinity. Okay. So this is saying that we have geometric decay in the tail of this distribution, meaning that a distribution, an offspring distribution in the subcritical regime will die out quickly. On the other hand, if mu is equal to 1, then the probability of extinction is asymptotic to 1 over sigma squared n, as n goes to infinity, where sigma squared is the variance of the offspring distribution. So in this case, what's happening is this is actually decaying very slowly. If the mean of the offspring distribution is 1, then this probability of decay is actually, it's larger for larger values of the variance. Okay. And you can think about why that might be the case. But the idea, so the probability that tau is large is going to be small, I should say. It's small for large values of the variance. Okay. And the reason for that, if you think about it, first of all, you can imagine a case where the variance is almost 0. And there's a limit to how small the variance can be, because we've assumed that we don't have a point mass at 1. But if we did have a point mass at 1, the variance would be 0, and we would never die out. So tau would actually be infinite with probability of 1. So we just have one individual replacing one individual in each generation. So if tau is very small, or if sigma is as small as possible, the next closest you could think about giving birth to 2 individuals or 0 individuals with some probability, with probably half each. Okay. So that's going to have some variance, and this is going to decay relatively slowly, about 4 over n. But if you imagine having, for example, a probability of 1 over 100 on 100 individuals, and 99 out of 100 on 0 individuals, then that's going to have a much larger variance. The offspring distribution will have a much larger variance, and the probability that tau is large should be smaller. And that makes sense because in order to survive even one generation in that case, you have to get lucky to kind of to give birth to 100 individuals. But even if you give birth to those 100, then one of those 100 is going to have to get lucky in the next generation, and so on. So that's just a little bit of intuition. The proof of that is in the notes. And then finally, I want to record something about the supercritical case, which is, well, something in general, but it applies to the supercritical case, which is the convergence behavior. There exists a random variable W, non-negative random variable W, such that the number of offspring divided by the mean at generation n converges almost surely to a random variable W as n goes to infinity. And in particular, if the offspring distribution has mean bigger than 1, finite variance, then the random variable W is strictly positive on the event that Cn goes to infinity. So it's the point there being that it's not a trivial random. It's not a trivial random variable in the sense that this convergence should somehow be well in the subcritical case. This convergence we might expect to go to some kind of constant and possibly and even actually to zero, because we're expecting the number of with probability 1 we know that the number of offspring actually goes to 0, but this will converge to some random variable in general, but the random variable will be strictly positive in the supercritical case. The way that this is proven, this uses what's called the Martingale convergence theorem, and this is proof that we would use the Martingale convergence theorem, which we haven't covered Martingale yet, so I'm going to refer to it. All right. So the next class of processes I want to move on to is called the Yule process, and it's a little bit different to the Galton-Watson process in the sense that what happens is, instead of having a random number of particles generated at each discrete generation, we actually have a fixed number of particles. So we start at time 0, we have a fixed number of particles generated, but at a random time. So there's a random time t, which is standard exponential, rate 1 exponential, and after that time t, the particle, there's a fission, binary fission into exactly 2 particles, deterministic binary fission. These are 2 identical particles to the first. So these are both identical particles, which will evolve according to independent unit rate exponentials, and they will undergo the same type of behavior. This is 5. And so on. Okay? And so the process in this case is going to be to imagine at any given time t, to look at zt, which is the number of particles alive at time t. And so in this case there are 3 particles. So this is a pure. This is what this is an example of what's called a pure birth process, because the number of particles is strictly increasing. It only increases as time goes on. Now, there's a few ways to generate this process and think about constructing the process, but there's a nice the tool that we'll use here, which turns out to be useful in proofs, is a Poisson process constructor. And one thing, so Poissonian constructions are particularly useful and in the study of Markov chains in general, continuous time Markov chains in general, and that a lot of continuous time Markov chains can actually be shown to be equivalent to running an independent Poisson process on some other space and reading off the jumps of the Markov chain from that Poisson process. And this is an example that we'll show here. So what we're going to do is, to generate this process, let's take some collection of independent Poisson processes with unit intensity. Okay, so each one of these processes, so we have occurrences happening infinitely many of these. So we have independent Poisson process happening for each of these cases. And so there are points occurring along these lines, and these are the occurrences of a Poisson process. And so what we've done at time, remember at time 1, we just start with an initial particle, and we wait for an exponential amount of time to branch that particle into 2. Another way of thinking about this is that every particle that's born lives forever and just splits off and gives birth to one particle at these random times. And then that particle lives forever from that point forward and branches off and branches. So there's two different ways of thinking about it. The way I initially described it was that the initial particle branches into two different particles, fissions into two different particles. Another way to think about it, which is actually more beneficial, and this is what we're using in this Poisson process construction, is that we have one particle that lives forever, and every particle that's alive at unit exponential times breaks into these other particles. So in this case, how do we relate that to what we just said? Is that we know that the arrival times of a Poisson process are exponential. In this, let's say unit rate Poisson process, and so that means that its inner arrival times are unit rate exponentials. And so we know that we first start with we have all of the processes running, but we only look down to the level at which we've had that many occurrences in the Poisson process so far. So at first we're only looking at this first one. We only care about the first one. And so this is all that the process looks like, is this. And then once there's an event, we start looking at the next available one. And so this is like the birth time of the second particle. And now we're looking at events in both of the first two. So this is now the next event, and so we start looking here. And now when's the next event? The next event is actually here, so we're still looking at all three, and so that's going to create a particle here. And then the next event that we see is this one here. So this is going to take us down here, and so on. Right? So what we're doing is that, if I can kind of fill this in, we're looking at the entire history of this one, and then we're looking at the history of this one after the first time that this occurs, after the first occurrence in the first process. Then we're looking at the history of this one after the first occurrence in either of the two that we were looking at before, and so on and so forth. So this actually gives us a copy of the original process, because the waiting time, we know that the waiting times in each of these processes are independent unit rate exponential. And so the waiting time for the third particle to be born, so in this case, what's the waiting time for the third particle to be born given we have two particles? Well, it's the minimum of two independent exponentials. So just remember that the minimum, so if we have x1 through xn are independent with xj having exponential rate lambda j, then the minimum of these independent exponentials is exponential with rate given by the sum of the lambdas. Okay, and that's all that we're using. So what we can do in this case is we can define a series of random times, Tn, to be the time of the nth occurrence, the birth of the nth particle in this process, which is the first time t after Tn minus 1, at which the number of particles in the okay, so what is this saying? So remember, we have, at this point, we have time Tn minus 1 is the birth of the nth particle. Birth of the nth particle. So that means that after the n minus first occurrence, we're looking at n of these paths, and then what we want to do is we want to say, well, what is the time of the next occurrence? Well, it's the first time, for example, after so if we look at this occurrence only, the time of the next occurrence is the first time in either of these two processes at which the number of particles that occurs in this region is exactly equal. That's the time at which we open up a new ring. And so that's what this is defined as. And then we can define the number of particles alive at time t to be n on the event that n is bigger than Tn minus 1 and less than Tn. So what we have is we have a sequence of stopping times. We end up with a sequence of stopping times for the construction of the process from the sequence of this collection of Poisson processes. And so that turns out to be helpful to us in studying the asymptotic growth rate. So we know that this is a growing process. It's a pure birth process. Particles only give birth to new particles. And what we want to know is the rate at which this, we want to know essentially the type of, how this process is behaving as the number of particles goes large. So the idea being that once we have a large number of particles, we should expect the behavior of the process to be pretty regular, because when we start with just an initial particle, there's a random time, and that time can be, it's an exponential random variable until the second particle appears, and then it's an exponential rate 2 particle, and so on and so forth. But as the number of particles grows, the rate at which events are occurring is also growing. It grows linearly. So with n particles, the rate of a new particle is n. And once we have a lot of particles, we should hope that that this process is somehow behaving regularly and converging to something. And so the theorem, it's actually pretty interesting for this, which in the notes is theorem 1010, is for a Yule process, with initial state 1, and this can easily be generalized to having any number of initial particles, because then we just have a composition of, if we start with 2 particles, then we start with 2 independent copies of Yule processes. But in this case, we start with 1 particle, and what we have is that e to the minus t ct converges to a random variable w with probability 1 as n goes to infinity, where w is actually distribution of W can be shown to be exponential rate 1. So what we have here is that ZT again is like a multiplicative process. The more particles that are alive at time t, the faster the process is evolving, because each individual particle is fissioning at constant rate 1, and so as a whole the system is fissioning, is creating new particles faster as the process grows. If we scale by the rate of growth, then we converge to an invariable level. And the way to prove this, so just think about by the Poisson process construction. So by the Poisson process construction, we can define a series of times, the inner occurrence times, tau n, to be the time between the arrival of the nth particle and the arrival of the n minus first particle, or the birth of the nth particle. So we define this for each n given equal 1. And so by construction, these inner occurrence times are independent, and they're independent exponential random variables. So actually tau n is exponential with rate n. So the expectation of tau n 1 over n, the variance is 1 over n squared. So the major observation here is that the sum, so the sum of these taus is a telescoping sum in the arrival time. So the sum of the first n taus is just going to give us the arrival of the n particle. Okay. So the sum, so the expectation of Tn is the expectation of the sum up to time n of the first n taus. It's a finite sum, so it's a sum of the expectations. The expectation of each one is 1 over k. So this is the sum of the first n values of a harmonic series, which asymptotically is log n. And the variance, this is just the variance of a sum of independent random variables, so it's a sum of the variances. And the variances are 1 over n squared. So this is the sum 1 over k minus 2. This is just converging to pi squared over 6, so it's converging to a finite value. Okay. So what that allows us to do is to actually prove that. So to prove this theorem, we're going to first make an observation, which is a more general observation. If we have xj we have a collection of random variables that are independent. So these are independent variables with mean 0. So they all have mean 0. If they don't have mean 0, you can just subtract off the mean, standardize. So they're mean 0. So in other words, they have to have finite, they have to have a mean in order to do that. But standardized, assume they have mean 0 and they have variances, finite variance such that the sum of all the variances is finite. Then the sum of the random variables exists so I define that limit to be S. It exists and is a random variable so it's finite with probability 1 having 0. Okay. Okay. All right. Okay. So to prove this, actually proving this, we will invoke the what's called the L2 maximal inequality. So the first thing that I want to show is what's called the L2 maximal inequality. Technical result, which is if we let x1, x2 be a sequence of independent mean 0 with same conditions as above, the variance has to satisfy this condition, has to have a finite sum. Then the probability that the sup over n of the Sn, so I'm defining Sn to be the partial sum of this sequence. Sup of the Sn's bigger than alpha is bounded by this. So this looks somewhat familiar from Chebyshev's inequality or Markov's inequality, but this is a statement for the sup of this sequence. And so what this is saying is the sup can't get too big, that somehow this finite variance and mean 0, this mean 0 condition doesn't allow the partial sums to get too big. And so to prove this, to prove this, we're going to use the wall again. We pulled up from another part of the notes. Remember earlier in the notes, earlier in the course, we showed the wall diagram, which is the evaluation of a random variable or a series at a random point, right? At a random number of terms of a sum of independent variables. And so what we're going to do is we're going to define a stopping time. So t to be the stopping time, which is the minimum of n such that Sn exceeds alpha, or we define t to be plus infinity if no such n exists. Okay. So clearly, if t is finite, then Sn, the sup, will be larger than alpha because we'll have a value of which is alpha. So the sup of Sn, the absolute value exceeding alpha, is equal to the event that t is finite. But this is equal to the event, the limit of these finite events. Okay. The increasing limit of events. Okay. So what we see here is we're going to apply the second walled identity, and we can do it to a bounded stopping time. So t min n is going to be a bounded stopping time, and the reason for this. So why is this there? We're going to apply the second walled identity to the sequence of bounded stopping times. Okay, so just to recall, second walled identity. So which we have right here, and I'm just copying from this. We have finite variance, and we have a mean, which we're assuming to be mean 0. Then, so if mu mean equals 0, then the expectation of st squared is equal to sigma squared, which is the variance of the first element times the expectation of t. But this is under the IID case, so in the IID case. So in general, this generalizes to the expectation of st squared is equal to this expectation of the sum from j equals 1 to t of sigma j squared. So that's for a stopping time, and what we're going to define here is that we note that for each n, t min n is a bounded stopping time. Okay, and therefore by the second walled identity, the expectation of the partial sum s squared at t min n, at the stopping time, is equal to the expectation of the sum up to that stopping time of sigma j squared. This is a bounded time, so this allows us to say, well, we know that this can be no bigger than sigma squared, which is finite, because the sum of all of the sigma j squareds is bounded. Okay, and so what we know is if we take alpha and we look at this statement, okay, st min n squared, indicator on the event that t is actually less than or equal to n. Okay. So this expectation, this value of s squared at t min n, if t is less than or equal to n, then s squared is larger than alpha, bigger than or equal to alpha. So then s squared, well, s is bigger than alpha, so s squared is bigger than or equal to alpha. And this expectation is larger than this event, this alpha squared, which is the smallest that s can be at the stopping time, assuming that the stopping time gets hit, times the probability of hitting it, okay, on the one hand. And on the other hand, this expression is bounded above by just the expectation of s squared at the stopping time, because this indicator only makes the value smaller, so these random variables are strictly is less than or equal to this one. But we know that this is just a variance. We've already shown that this is bounded